Welcome to our final installment of Saturday Engineering for Everyone. I appreciate everyone being here on a beautiful Saturday morning. I know that there are also a few competing engineering events going on around campus, including a robotics contest up on the south side of campus. I believe they're doing that at the ARC today. And so I really appreciate everyone showing up today, and I encourage you to, if you have time, go enjoy some of the other engineering going on. So it's a real pleasure to have Brian Cunningham here today. Brian is an old friend, and more importantly, and probably the highest honor I think I can give him is that he has his PhD from the University of Illinois in 1990 under very famous and esteemed professor Greg Stillman. Brian went out into industry and spent 15 years out in the world making stuff and making the world a better place, including by founding his own company, SRU Biosystems, who, under the auspices of that company, developed analysis tools for drug development, for pharmaceutical development. And Brian came back to U of I part-time in 2000 and then joined as full-time faculty a couple of years later, has been with us ever since, and is currently the director of the Micro and Nanotechnology Lab right next door, and a professor in electrical and computer engineering and bioengineering. Today, Brian's going to talk to you about teaching your old smartphone new tricks, mobile biodetection for health and food safety. And I'm going to let Brian get started in just a minute. Before I do, I just wanted to say thanks to a few folks who have been with us over the years here. First of all, our speakers, all of them, and I'll get back to that in a moment, our EC Communications folks who every time we do one of these, gets the word out and lets you all know this is going on. Our longtime friends over in physics, Tony Pitts is here today. Hi, Tony. And, of course, Inga Karliner. Hi, Inga. And then the undergrads who really keep the wheels greased here. Ian Brereton, who's sitting in the back, one of our star students, and another one of our stars, who's, I believe, actually out doing the hard work, keeping this thing running. Sneha Ramanarayan. And then the department who makes this happen, brings us this building and lets us use this space. My department and Brian's department, electrical and computer engineering, our building staff, our department head who's been supportive of this series for 2 years now, and the student chapters who set up outside over the last 7 lectures, Inspire, the OSA and SPI student chapters, and today the Society of Women Engineers. Again, if you didn't have a chance to talk to them on your way in, please take the time to talk to them on your way out. They're great kids, and they're here doing great stuff. And so lastly, I got
you covered with this.
Man, it's high technology. Brian's way ahead of me on this stuff. We have, I'd like to thank all our speakers over the year. This year's speakers have been extraordinary, except for the second one. And then, of course, we culminate with Brian today, and it's no coincidence that I put Brian in the anchor position. We're hoping to get everyone to come back next year, and I think when we do this again, and Brian's the best way to do that. And I'd like to thank the speakers from last year, which was the inaugural year of Saturday Engineering for Everyone, and all of them, with the exception of Gary Eden, and we're going to make Gary come back and do another one of these as a result, are available on the website for the series. The videos of them are available on the website. I was just told that the videos are locked for people who come from outside the university, and so we're going to get that fixed if you ever want to go back and look at any of these. So without, and I do have one more thing. All of our speakers have put in a tremendous amount of work to make this happen, and as a result, I thought we should say thank you in some way, and so we've got these for everyone who gave one of these talks, but Brian, I'd like to present you with a framed copy of your talk poster for today. Thanks, Brian. The stage is yours.
All right, thanks very much. Thank you very much, Scott, for organizing this series of lectures, giving the faculty a chance to share what we're doing with people who aren't students at University of Illinois, and really have a chance to share what we do with people of all ages and backgrounds. And I have to say, it's a little bit of a challenge putting together a lecture that understood by everyone. So I hope I'm successful at that. Thanks so much for coming on a beautiful Saturday, and we'll get you out there for enjoying your gardening, bicycling, running, and all that good stuff. But I appreciate that you came here today to learn something about biosensors. So our work is motivated by a lot of different things. And so I know many of you have had blood tests where the phlebotomist takes sticks a needle in you, takes out several milliliters of blood. What happens to that blood? Well, it goes into the basement of the hospital or gets shipped to Mayo Clinic or somewhere else in the country where trained laboratory technicians will perform tests on it, mix liquids together, put the thing into the detection systems that tell you the result of your blood test for whatever the doctor happened to order for you. But there's an interest in being able to take those capabilities so that tests could be done at places closer to where the patients are. So, for example, tests that could be performed in the doctor's office, in your home, at a remote clinic in sub-Saharan Africa, or perhaps in the intensive care unit of the hospital where you can get the results immediately. So to make this thing happen, which we call a point-of-care diagnostics, you have to have a test that's automated. You can't have a trained technician doing it anymore. And so people make small plastic cartridges that have little valves and pumps in them that can move liquids around and do the things that the technician would have done, but now do them automatically. The detection system shouldn't cover an entire or fill an entire room, but be small, maybe even handheld or the size of a shoebox. These things have to be inexpensive. When people talk about the cost of a test, it needs to be like $5 or less. And so the items that are used for the test, the biological reagents, the thing that holds the liquids and does everything, usually they have to be made out of something cheap, like silicon or plastic or some combination of both. And now it's even more exciting that with the internet, you could imagine having a test performed here, the results being communicated to somewhere remotely, where perhaps a computer algorithm will sort through the data, do some analysis. Perhaps a doctor somewhere else could look at the results and send their interpretation back to you. And so the person doing the test doesn't have to be the expert at that test anymore. They have to be able to carry it out. But the interpretation and reporting the result could be done by someone somewhere else. We're also interested in applications not just in health, but in food and drug safety. And so if we think about all the things that you might want to test for that are important to our health, so for example, you're detecting viruses in groundwater, and so managing or knowing about viruses that are being generated in food or animal facilities, that animals, what do? They eat and they poop all day. And so the things that come out of the animals end up in the groundwater. And so we're interested in testing for them before we irrigate crops or drink that water. Many of us have allergies to food, especially peanuts, but many other types of allergies. People are interested in detecting things in food before they consume it. In agricultural applications, there's toxins in grain that can grow if the grain isn't stored in the right conditions. That in fact, those tests need to be done at the grain silo and be done immediately, even while farmers are unloading their grain before it's being stored. And so, not even possible, to take a sample, send it to a lab, and wait a couple days. They need to have tests that are done immediately out there in the field. And same thing in quality control in food manufacturing. So I think we should acknowledge that our food is actually manufactured in factories a lot of the time. Those places are getting ingredients that come from all over the world. They want to be able to check and make sure those ingredients are pure, not contaminated with other things, that no unscrupulous person made a substitution somewhere along the line. And so food testing in food manufacturing, tests that can be performed at the loading dock or in the factory are very important. Also, we're concerned about tests that can be performed to measure things about the environment. And so people are interested in knowing if pesticides, fertilizers, things are like running off of farm fields and getting into groundwater. People are interested in detecting all sorts of things in water resources, lakes and streams and and even oceans, if you consider measuring whether it's safe to go in the water at the beach that might be contaminated with bacteria. And so there's even applications in buildings and in biodefense where the soldiers are concerned about being attacked by someone with a chemical or biological weapon. They have to be able to perform tests on the environment where they are at that moment. They can't take a sample and send it back to the lab and then find out later that they were attacked with a biological weapon. They need to be able to respond immediately. So what we're seeking to do in our research is to take the capabilities of these laboratory instruments that cost tens of thousands of dollars, in some cases the cost of a nice car or even a pretty nice house. But these are detection systems that the biologists use to detect things, and they're expensive and big. And so what we're working on is taking all the capabilities of these detection instruments and building a small cradle that interfaces with a smartphone that allows the phone to do the same sort of things. And so that's what I'd like to tell you about today. The approach that we use is all based on light. We're using the back-facing phone in a standard iPhone 4, but you can use other phones as well. But we started this work when the iPhone 4 was new and cool, but now it's there's two more after it. But the basic idea is that we're using the camera and the phone to measure things about light that allow us to do these biological tests. And so what I wanted to do was to describe how we do that, but we need to go back a little bit and talk about light and exactly what it is. Let me ask who's heard that light is a wave? So most people know, but not everybody knows that light is a wave. So exactly what does that mean? Well, what kind of waves are we already familiar with? Well, we've all taken a bath or gone to the beach, and so we know what a water wave is. And so what are the things about a wave that we can measure? Well, if we look at the distance between two high points in a wave, we could call that the wavelength. And so we'll see how light also has a wavelength, but other types of light or other types of waves all have a wavelength. Also, you can measure a wave by how big it is, how much energy that wave has. A big wave you would use for surfing would have a big height. A more nice wave in your bathtub would have a smaller height, representing how much energy is being transmitted by that wave. So if we think about a wave, what I'd like to do here is click on this. Hopefully it will work. Yeah, so let's think about what's actually waving in a wave. So if we were able to zoom down to nanometer size and look at the water particles in a water wave, let's just follow these two guys here that are in yellow. The water particles themselves aren't really moving too much. The wave is moving from left to right, but the stuff that the wave is made out of, the water itself, actually not traveling very far at all. Each individual one is knocking up against its neighbors, but the propagation of the wave only means that the things inside the wave are moving a little bit. Okay, so we can measure a wave by its wavelength, by how big it is, what we call its amplitude, and then also we can think about how fast the wave is going up and down. We call that the frequency, and these things are all related to each other. Another type of wave that we can easily visualize is just a jump rope. So if you and I hold two different ends of a rope and we wiggle it up and down, we can make what's called a standing wave. The rope isn't going anywhere. We're holding both ends of it, but the little pieces, each little piece inside the rope, are moving up and down. And so again, if we move our arms a lot, we can generate a wave that has a big amplitude. But what you would see is that different parts of the wave, if you were to track just one piece of it, it would be going up and down and up and down, and it would be doing that at some rate. That rate is what we call the frequency. Okay. So let's think about a couple of different types of waves, and I'll get to talking about the type of waves that light is made out of. And so one type of wave that we call a transverse wave is a wave in which the like the jump rope wave, the wave is moving back and forth, but the piece of the jump rope is going up and down. So the motion of the piece of rope is in direct direction that's different than the direction that the wave is moving in the jump rope. So we call that transverse. Another type of wave is a sound wave. If we think about what happens in a sound wave, it's a little bit different. Yeah, so here's a sound wave. So let's imagine that I have a speaker, like a little plastic membrane that I can move back and forth. It moves back and forth and pushes the air in front of it. And so again, if we look at one particle of air that carries a sound wave, the air itself isn't moving. We don't have wind being generated in the room. But what we see are some places where the air particles are mashed up together and other places where they're spread further apart, and that the compressed regions are what moves. So again, the wave is moving. The sound wave is going from where the speaker that compressed the air to the other side of the room, but the air particles themselves not really moving too much. And so this type of wave is different from the jump rope wave because the direction of the moving particles is in the same direction as the moving wave. And this is called a longitudinal wave. Okay, so the way that we hear sound waves, I have to get my pointer back here again. Where is it? There it is. Okay, so the way that we hear sound waves is that these compressed and less compressed regions of air reach a membrane in our ear that moves it back and forth. I mean, this movement back and forth stimulates nerve cells in our ear, allows us to actually hear the sound wave that comes up against it. Okay, so now I wanted to use sound as an example because it's something that that we can experience in everyday life. What I wanted to talk about was the speed of sound. And so if I stand over here and yell as loud as I can, it'll take the sound from my mouth 1 second to travel 4 entire football fields. That's gives you an idea how fast sound moves. So you can even tell that if you've gone to the Illini football game, if one side of the stadium is going ILL and the other side is going INI, you actually see the people moving before the sound reaches you, and of course that's because light travels faster than sound. So the speed of sound in air, 343 meters per second, so pretty fast. But sound can travel faster through other things. So if you have sound traveling through water, it's 1,500 meters per second. In metal, it's 5,000 meters per second. So what's the reason for this? How can sound move faster in one thing than another? Well, it has to do with the material. And so if you think about air molecules, they're not very dense. We can walk through them, of course. Water is more densely compressed molecules than air is. We can still swim through it, though. But molecules that bump up against each other can do that more rapidly in water than in air. And then, of course, metal is really dense. We can't move through it at all. Metal atoms are all compressed up against each other very tightly, and so sound can move through that material much, much faster. And so with sound waves, again, they have frequencies, playing different notes on a piano or different pitches and tuning forks. Each of those, each tuning fork represents a different frequency, a different note that we hear, even though all the waves are traveling approximately the same speed through the air. Okay, and then of course with sound, if you're depending on your age, you can hear different frequencies. The lowest notes people can hear around 12 waves per second. The highest pitch notes people can hear around 20,000 waves per second. Okay, so I wanted to talk now about differences between different types of waves. And especially I wanted to get to light waves and what actually all waves are made out of. And so if we think about these different types of waves and what they have in common, I can get this here. Yeah, so if we're like a line of people, we can do the wave. The people aren't moving, but you can see the high point of the wave moving from place to place. Again, with a sound wave, we have air particles or water particles pushing up against each other, and the wave moving from place to place. With our jump rope wave, that's an example of a transverse wave. We wiggle the rope, and the wave moves down the rope. So what all these things have in common is that the wave is moving through something. We actually have a rope, or we have people, or we have air molecules. That's like the thing that the wave moves through. And this is where light waves are very unique and very special compared to other types of waves. Okay, so light is a wave. I said that at the beginning, but we don't see it waving. We don't actually when I shine my laser at the screen, we don't see light. We don't see air particles moving around. So light has a wavelength as well, but the reason that we can't see it is not actually because the wavelength is small. So I wanted to give you an idea of the size of wavelengths of light waves and kind of give you an idea. We're going to be talking of units of nanometers. 1 nanometer is 1/billionth of a meter. What does that really mean? And so let's think about things that are small. So grain of sand, that's about 40,000 nanometers for just one grain of sand. One red blood cell, about 7,000 nanometers. One virus particle, those are really small, about 20 nanometers. So if we think about things that are small and compare that to light, let's see how that works out. So here it shows the spectrum of light, where light is actually comprised of many different wavelengths, going from pretty big, like measured in meters, all the way to really tiny when we think about X-rays and gamma rays. And the light wavelengths that we can see, and the ones that are detected by our smartphones, are in the visible part of the spectrum. That's so we can take photos of ourselves and our lunch and our friends and everything. So the wavelengths of light that we can see range from around 400 nanometers to around 750 nanometers. What's out here is what we call ultraviolet. When we go below this set of wavelengths, we can't see them anymore, but they can still give us a sunburn. If we go above these wavelengths, that's called infrared. These are our wavelengths, like our TV remote controls work in those wavelengths, so we don't actually see beams of light coming out of our remote control, but it's still light that is carrying that energy. And so just to give you an idea that all these things are actually light, even though we don't always think of them as being light. So for example, radio has a wavelength of around a meter. This is what makes our Wi-Fi work, so that's very important. So I'm not sure if you listen to the radio, FM or AM, that's in the meters, but also Wi-Fi doesn't work without radio. Our TV remote control in the near infrared, around 1,000 nanometers. Visible light in this range, 400 to 800 nanometers. X-rays, when you get X-rayed at the doctor, a wavelength of that is 0.1 nanometers, so even smaller than the virus. So this just gives you a sense of how light covers many different sizes. Only some of them are wavelengths that we can see, and these are really small. So the unique thing about light waves compared to all the other types of waves that I've talked about is that light waves don't need a material to move through. And so this is actually like very strange. And people wondered for centuries, what is it that light moves through? They had some mysterious thing called the ether that they postulated existed, even though no one knew what the ether was. So it's actually fortunate for us that light can travel through nothing, like outer space, because that's the only reason that energy from the sun can reach us and not have us have a super cold planet. And so the fact that light can move through nothing actually important for our existence. So light is so fast that people didn't even really know for a long time that it moved, that it actually had a velocity associated with it. One of the first experiments, actually the first experiment to measure the speed of light was done with a candle, shining light against a mirror and bouncing the light back against a mirror that like rotated, and looking at the change in the angle of the light that bounced back compared to the angle of the light that came in. They were actually able to get a pretty good estimation of the speed of light using a candle and a fast rotating mirror. This distance was actually really big, so that they could have this light go really far, make a long trip, and come back, so that the mirror was in a slightly different position by the time the light came back. To give you an idea, it takes about 8.3 minutes for light leaving the sun to reach us here on Earth. And so that works out to a speed of 3 times 10 to the 8th meters per second. So light's pretty fast, but can anything slow it down? Can anything alter its speed? Light has its fastest speed going through outer space or through a vacuum. But in fact, light goes slower if it goes through anything else. And I'll talk about why that happens. So how can we see light slowing down? A demonstration that I've done with kids in class is to have them stand in a line and hold hands and have a line this way that represents where if you're on this side of the line, you walk fast. If you're on this side of the line, you walk slow. And so the line of people, as they approach this person starts walking slow first, then this person starts walking slow second, and what you see is that the line changes directions. And so the line of people would kind of go from this way, and they'd end up changing directions and going that way. And so this is actually what happens with light waves as they make a transition between a place where they can move fast and a place where they move more slowly. And this is what we call refraction. This is the basic reason why if you look at a glass of water with a straw in it, it looks like the straw changed directions or has a break in it. It's because the light is traveling at a different speed in water than it does in air. We can see this more clearly if we take something like a glass prism. So a chunk of glass has a slower speed of light than air. And if we take white light that has all the wavelengths in it all combined together and shine it into this prism at an angle, the different colors of light will start to refract at slightly different angles. And the reason for this is that the speed of every color is not exactly the same for light traveling through glass prism. And so in this way, some light will refract at a shallow angle, some light will refract at a bigger angle. If they travel enough distance, they'll separate from each other. And then by the time they come out the other side of the glass prism, now each component of light, each wavelength, will be traveling in a slightly different direction. So what is actually waving in a light wave? Let's think about that. So first, the thing we need to think about is something called an electric field. The basic idea of an electric field is that it's something that can apply a force to something that has a charge in it. And so we're familiar with electric field like from a battery. A battery is something that if you connect the positive and negative terminal to something, you have a positive side and a negative side. And so a negative charged thing will get attracted to the positive side terminal of a regular battery. And this is basically how we draw energy out of a battery that can go through a light bulb, heat up the filament inside, and give us some light. So what has an electrical charge that we can apply a force to with a battery like this? Well, it's electrons. Electrons are, the metal in a wire is loaded with electrons, but of course they're really small and we can't really see them, but everything in the world that has an atom in it also has electrons in it. So electrons really everywhere, even though we can't see them. And so if we think of a molecule we're all familiar with, such as water, water's got an oxygen and 2 hydrogen atoms, and it's also got a cloud of electrons that are going around those oxygens and hydrogen atoms. And so let's think about what would happen if we take like one molecule of water and we take our nano battery and we put a positive and negative terminal connected to our battery, our electrons would get sucked up to, into the positive side of the molecule. So negative charged electrons will get repelled by the negative side of the battery and get attracted to the positive side of the battery. So the electrons are still in the water molecule, but now the water molecule is a little more negative on one side than on the other. And so now let's say we take our battery and we can rotate it around like this. We have a battery that turns, so we can change what side is positive and which side is negative. We can just flip it over and over really quickly. So making one flip from positive to negative and back to positive, that would represent one wavelength of an electric field. So if we can imagine doing this with a nano battery, if I can show this, what you'd get is this orange thing represents a positive and negative going electric field. It's kind of like the jump rope, but now what we're doing is changing the charge on our battery, going from positive to negative over and over again. And so you're changing the charge and doing it in a repeating kind of way. Now, if you come to University of Illinois and take electrical engineering class, we'll teach you all about this. It's Scott's specialty, is the way that electric field can move and move through nothing is that an electric field represented in orange can join up with a magnetic field represented in blue that both oscillate at the same time. And so, in fact, because this electric field and magnetic field are together, it allows this wave to move from one place to another, but not need anything. It can move that way through vacuum. This was something discovered only about 150 years ago by one of our heroes in electrical engineering, James Clerk Maxwell, who was the person who understood this first and developed a set of equations that we worship and study and do all sorts of things with in electrical engineering. Okay, so let's imagine now we can take our waving electric field and we can apply that waving electric field to a molecule like water. So the electrons in that water, what are they going to do? They're going to be faked out. They're going to see this changing electric field, and they're going to start to wiggle up and down. And so they're going up and down. They're not leaving the water molecule, but they're wiggling. So the thing is, with electric fields that travel through things, everything except vacuum has atoms in it, and all that stuff has electrons in it. And so the basic idea is that if you have a waving electric field, and it has to go through some other material, and I think I wanted to hit this. So if we have light that goes through a vacuum, it can just travel on its way. Oops. I have to get this to happen again. There we go. So if we have light that goes through a vacuum, it doesn't have to interact with any electrons. But light that travels through water molecules or anything else actually has to slow down enough to wiggle the electrons in all those atoms before it can move on to the next atom in its chain of moving. And so if we had a race between a electric field going through nothing and an electric field going through some material with electrons in it, it will always go slower through something that has electrons in it. And the reason is it has to slow down enough to wiggle all those electrons. Okay, so now let's think about what colors are. So again, colors represent the visible wavelengths of light going from 400 nanometers to 750 nanometers. They travel approximately the same speed of light, same speed in air, but they travel at different speeds going through some material like glass. And so if we, like I mentioned, if we take a glass prism, shine white light at it, and the light will get dispersed into all its components, and you'll be able to see the rainbow on the opposite side of the prism because the prism has separated out all those wavelength components. And so we can, as you know, we can make different colors different ways. So even with the demonstration outside with the students we're performing today, you can take different color lights, like red and blue, combine them together to make magenta. You can take yellow and magenta light and combine them to make red. So you can make different colors of the rainbow by taking individual colors and combining them. But I wanted to talk about a different way that we get color, such as like things that are painted. Why is a red house red? Why is a blue car blue? They're not light generators. They don't like produce blue light unless you have a fancy car covered with blue LEDs or something. But they reflect light. So if we take white light that has all colors, what the blue paint is actually doing is taking the red and green colors and absorbing them. So the blue color is the only one reflected. That's the one that we see. Same thing if you look at a red house, the red paint actually absorbs blue and green colors, and the red light is the only one that's reflected off the surface. So that's how we actually see different colors of things that are painted. What about colored liquids? It's kind of the same thing. If you have a green, like Mountain Dew or something, or maybe like chlorophyll is something, a green substance in plants that plants use to absorb light. If we look at the light, if we shine white light in and look at the light that comes out the other side, some wavelengths will be absorbed by that colored liquid. So a green liquid looks green because the red and the blue wavelengths have been absorbed in that material, and the green light was the only stuff that could make it through the other side. And so same thing with other colored substances. That's how we actually see them and perceive their color. So finally, I'd like to get to what does this have to do with smartphones, and how do we use this for doing all these sensing things? Well, we developed a system that allows you to take a white light source, such as from a light bulb or of the white light LED in a camera, and we can pass it through a substance and measure the wavelength components that make it out the other side. The way we've done this is to make a small plastic, or in this case, our first one was made out of aluminum, cradle that interfaces with the back-facing camera in an iPhone 4. And rather than having a prism, because that would be really big and bulky, we have a different component that's called a diffraction grating that's small and flat that we can place right in front of the camera's opening on the back. And that diffraction grating does the same thing as the prism, that it'll take the white light and to split it into all its different components and spread them out against all the pixels that are in the sensing part of the camera. And so if you take a white light and put it through this diffraction grating, we do some computer simulations to show that the light comes in and that we have to consider the opening, like what we call the entrance pupil of the camera itself. So this line here represents the back of the camera. There's a lens inside there, which we have to know a little bit about. But then the light will be spread across all the pixels of the camera that's on the inside of the phone. And so this basically allows us to have a handheld thing that does the same thing as one of these expensive and heavy instruments. Here at Illinois, now you can take classes on how to create your own app. And so students that are interested in making the next Angry Birds or the next Candy Crush or whatever can take a class and learn how to do that. We had a group of undergrads that wrote our first app for using an iPhone to do biosensing work. And I'll show you just what this does. So what we call a spectrometer is an instrument for measuring the wavelength components of light. And so what we can measure with this thing is if we take a picture with the cell phone when it's in this cradle, instead of getting a picture of the outside world, you measure a spectrum instead. And so if we take a green laser and point it in, we get a little green line in our image. If we take a picture with a red laser pointing in, we get this red line. If you have white light, you get this whole spectrum spread out across the pixels. And so, this blue line represents the wavelengths from a white light source, like a light bulb, measured with a real spectrometer. This is what we measure with the smartphone. The phone actually puts some emphasis on other colors, on some colors more than others. Maybe that's to make our skin tones look better or something, but the phone actually puts this shark fin characteristic in there. And so if I take something that absorbs light and stick it into the optical path, I'll see a little band, like a dark band of wavelengths that are removed, and I can measure that like dip in the spectrum used by looking at the output of the pixels measured on the phone. And we can do this with a real spectrometer, or we can do it with the phone and measure the same thing. So this just shows an example of how we measure colored liquids using the phone. So if I take red food coloring and I put it into the optical path, we would have, ordinarily, with no red food coloring, you would see all the wavelengths, but red food coloring absorbs green and blue wavelengths, and so as I increase the amount of food coloring, we see that the spectrum changed from this black line down to this blue line. We've just like cut off and removed all the red and blue components. Same thing with green food coloring or blue food coloring. We can remove whatever component that we want. I wanted to describe how we use this for doing biosensing. First, say a couple words about proteins. So proteins are in lots of things, in our milk, in our bread, in our meat, and so on. So proteins are not only in food, but they're in like biological organisms like ourselves, plants and animals. So if we think about what a protein is, here's a milk protein called prolactin. It's a whole bunch of atoms all glommed up together. These atoms contain just loads of electrons, way more than a water would have. So you can imagine that if you were an electric field waving, there would be a giant bunch of electrons in here that could wiggle back and forth. And so these absorb light and slow down light very substantially. There's a special protein called an antibody, which are molecules produced by our immune system. An antibody protein looks a little bit like a Y shape. It has like two arms like this. The action part of an antibody is actually on these hands that allows an antibody protein to bind with and capture only one specific type of molecule. And so if we're, say, exposed to the flu, our immune system will generate antibodies that have little lock and key attachers on the end that can attach to the flu virus and remove them from our system. If the flu is different next year, then the antibodies in our system will be created new to have different arms to recognize that different thing. So the key thing is that these antibody molecules are really specific in what they can attach to. And so there's a biological test. It's actually called a sandwich assay. And it's not because it's delicious, but rather it's because we can put an antibody on a surface, and that surface can then be used to capture one specific protein out of a test sample. In order to detect it, we have a second antibody that attaches to a different part of that same molecule that has something that will generate a signal that we can measure. So I'll show you how that works in just a second. So this thing is what we call the analyte. It's what we're trying to detect. This represents the peanut allergen or the cancer biomarker or the thing we're trying to learn something about. So if you had a blood test taken at the hospital, the test that was performed on it was probably something like this, where they have these little plastic cartridges that have a transparent liquid in them. The cartridges all have antibodies stuck to them on the bottom. The antibodies are exposed to your blood sample. The thing they're testing for will get grabbed by the antibodies. Then they'll have a second antibody making this sandwich that has something special attached to it that will generate a purple-colored liquid. So the more of the analyte you're trying to detect is present, the more purple the liquid will change. So it starts off being clear, but then the concentration you're trying to detect is related to how purple the liquid gets, and we can measure that by the absorption. So the absorption, that's the thing, like the colored liquid, that we can measure with our cell phone. Yes, yeah, question? Oh, there you are.
Is that why they usually take more than one blood sample? Because they have so many tests, individual tests they have to run?
That's right. So they'll take your blood sample and they'll subdivide it into lots of different smaller aliquots and then perform one test on each of them. And I think they're just greedy too. They just like sucking blood out of you. I don't know. So So this is an example. This is like the first test that we did using our smartphone to do a test for a protein called interleukin-6 or IL-6. This is a protein that's used for cancer diagnostics very frequently. And so this is what IL-6 looks like. It's a protein. It's big. It has all sorts of electrons in it. The basic idea here is that the more IL-6 was present in the sample, the more purple the liquid gets. And so we see the absorption going from small to big. And so we can see very clearly the liquid getting more purple, and we can measure the whole spectrum of using that system that I showed you. And so we performed the test using our phone. We also did the same exact test using the laboratory system and got the limits of detection, like how low we could go, detecting around a picogram of that substance in 1 milliliter of liquid. The picogram is 10 to the minus 12, so it represents not very much. This is a very, very sensitive test. Another such test, very similar, is one that can be performed for the peanut allergen. And so let me ask, who has peanut allergy? Nobody? Oh, that's amazing, actually. So if you have peanut allergy, there's a family of proteins called ARA, H1, and H2, and H6. There's actually like 12 of these that are the proteins, like shown here, that people are sensitive to. ARA, H1 is this one, is actually the one that people that have the most severe peanut allergies have an allergic reaction to. And so being able to have a test for peanut allergen, very important. And there's antibodies to the peanut allergen, and a test that can be performed likewise that changes a liquid from clear color to colored. And so the test that we did was to take cookies, mix them with hot water for about 10 minutes, let the cookie solid stuff settle to the bottom, and then we take the juice, like the cookie juice, and performed our test on it. And so what we showed is that we could perform a test for the peanut allergen by measuring the color of the liquid with our smartphone with the same way that you could perform it with the laboratory test. And we went to the store and just tested this on real cookies, some of which are supposed to not have peanuts in them. And so if you go to Insomnia Bakery, they don't have separate facilities for their peanut butter cookies and their sugar cookies. So their sugar cookies, actually, we found them to have a lot of peanut allergen in them. The peanut butter cookies, just forget about it. They were off the charts. If you go to Schnucks, though, and get sugar cookies, they actually make them in a separate facility. And so the level of peanut allergen in Schnucks sugar cookies are pretty good. Oreos, you're also safe. So again, this is a 10-minute test that we perform with a couple of reagents, and in the end, end up measuring the color of a colored liquid using the phone.
Can you go back to your previous chart?
This one here.
They don't look the same.
Yeah,
You're trying to show that the laboratory and the smartphone are giving you the same answers, but it doesn't seem obvious on those graphs.
Yeah, I apologize for that. It just has to do with the red line is the curve fitting. When you go in and perform the test, the first thing that we do is we actually put the peanut allergen into the test sample and measure it at 4 different concentrations where we know the concentration. And so these curves represent the different concentrations. Then we just fit this to a line. What we really care about is that there's some difference between these concentrations that represents like the range that we're interested in like diagnosing or measuring the peanut allergen concentration from an unknown sample. So as long as we have a difference between the low and high, we're in pretty good shape. We fit this with a curve so that we can interpolate between the points. Okay, so actually one of my students is here today to demonstrate this. We've moved since doing our iPhone work to a Samsung Galaxy phone and developing our own app even further for this. I wasn't sure whether we could do this on the table and we could see it by video, or whether we should just do it afterwards and anyone who wants to see it come up and see it live without the camera. This is our, what do you think? Can we do the camera method? Pardon?
You can do it now if you'd like, that's fine.
Okay, so you're on. Yeah, so do you have like zoom in ability?
Hi everyone, my name is Lee. So today I will do a demonstration with Samsung Galaxy S3.
Oh, okay. Tell you what, here, put this on you. Yeah. So put that on your belt. Let's put this on you. Right. You did.
Hi.
Yes.
Here we have Samsung Galaxy S3, and this is the cradle we designed to hold the smartphone, and also it has fiber optical part in it so that we can get the light. So here I have water liquid. So when I put it in here, you can see that we have a full spectrum of red, green, and blue. So then I will take a picture of it. It's doing averaging image because our detection have noise in it. So, and it is processing the spectrum right now. So we can see that here we have a spectrum of red, green, and blue one, and the black one is we just sum the total of spectrum here. So here we will demonstrate with the sample.
I think that people probably can't see it, but if you like to come up afterwards, we can show you. You can actually see the screen and what's going on. So they can't zoom in any further with the camera than that.
Yeah. So this is with the red sample. So because blue and green get absorbed, so we only see the red spectrum here. It's doing the same thing that we did before. And finally, we have the spectrum of the sample and also spectrum of the white LED, and we can measure the absorption here by subtract the reference by the sample.
So I've been told we have something called a document camera. You can you can put the thing under that, and we can display it. It should look really clear.
Yeah.
So while they set that up, maybe I'll just go bring it over here and set up here. And then while you do that, I would like to acknowledge the graduate students in my group. They're the ones who did the things that I described today. So we have students in bioengineering and electrical and computer engineering, even some material science and physics students that participate with us. And we've been really fortunate to have great collaborations with biochemistry and molecular biology people to help us learn about what's important to look at. And then we've got funding from this work from National Science Foundation and NIH for not only this project, but we're working on other things that involve detecting infectious disease. We have another project for detecting fraudulent drugs that are distributed in developing parts of the world that have been diluted or replaced by other ingredients. So in all the work, really, we're focused on how to use the inexpensive nature of cell phones, the fact that everybody has them now, and that you can build very inexpensive systems that interface with a camera inside them to allow the camera to do all sorts of interesting tests. Oh, so I think you're ready? Okay.
Yeah.
Okay, so hopefully you get see what the app screen looks like when we do a test. I think we is just putting in different colored liquids with food coloring, and then so you can see measuring the spectrum. Okay. Cool.
They can still hear you in here, but the recording will be a little bit less.
Yes.
Once you developed this for the, you said you started out with the iPhone 4. How difficult was it to adapt this, once you figured out how to do it to different iPhone or other cell phone technologies? Was that difficult?
Yeah, so the biggest problem we had with using the iPhone is that the operating system doesn't allow us to really get in and change things for even controlling the exposure time of the camera and things like that. So that led us to change to Android phones. Like you say, your phones change every 6 months. They keep coming out. Actually, they keep getting better for us because we started with a 4 megapixel camera. Now they're 16. The more pixels means better spectrometer for us. It has better resolution. And then the phones keep getting better for low light photography, which makes them more sensitive for seeing really low optical signals. So we're taking advantage of that as well. In the work we're doing now, in the cradle that we make them by 3D printing out of plastic. And so we can change the design, print out a new one to adapt to whatever, like the location of the phone's camera or the location of the back-facing LED. Or the size and shape of the thing, we can adapt to any phone pretty quickly now.
So you have to break it down for me a little bit. Is it like a recipe? Like if I wanted to make chocolate chip cookies and I wanted to change my chocolate chip cookies, I might add more chocolate chips or butterscotch chips. How do you, once you get that technology, what do you go through to make it work for another type of phone? Do you have to write new programs? Do you have to measure differently?
Right, so as long as it's an Android phone, the operation be very much the same. Although if we were really developing like a product, we'd have to do the same thing that the companies do that make apps that work on everybody's different phone, that has subroutines that can adapt to the size of the camera that particular phone model has and things like that. So in our work here, we're focused on one model phone. If it was to be a product, it would have to be, the software would have to be written in a more robust way to include like all the possible combination, like types of cameras that could be inside the phone.
Is this something that would be available to consumers at some point?
I hope so at some point. We're not working on commercializing it right now, but there have been companies that have expressed some interest. So we're currently working more in a research mode, but perhaps in the future. It's hard to say how long it might take. Yes?
Where do you get the antibodies to form the little sandwich to make the water turn different colors?
Yep. So the antibodies, we actually buy them. There's companies that have gone through a lot of work to create these antibodies. What they do is that they take the antigen, the peanut allergen, and they inject it into an animal. And then the animal's immune system develops the antibodies. Then they suck the blood out of the animal without killing it, and then filter out the antibodies and purify them, and then sell them to people like us. So there's kits already for thousands of things, like the IL-6, like the peanut allergen for HIV virus. There's antibody kits for many, many things that we can take advantage of using the system.
While Brian is answering a couple of questions, are there any kids or people with kids at home in the audience who did not pick up a raffle ticket? Okay, did everyone get a raffle ticket? So as you may know, we've heard mentioned at this series, this is the International Year of Light, and the Optical Society of America put together this nice little light blocks kit that the OSA student chapter was doing demos with outside. And so we're going to pick a few winners and give a few of these away while Brian takes a couple more questions, and I'll interrupt you again in another question. Thanks, Brian.
Okay. All right, the raffle, yes.
During the height of the Ebola epidemic, we read in the media that someone had developed a small portable test,
Mhm.
antigens. Is that based on, do you know whether that was based on this technology or not?
Well, they likely used an antibody for that test. I'm not sure specifically what test you're talking about. There's two types of tests that could be used for Ebola. One is based on detecting its DNA. So it breaks apart the virus, sucks out the DNA, and then amplifies the portion of DNA that is specific to identifying Ebola. So that's one type. And then another type is like this, where you have an antibody that recognizes an outside protein on the Ebola virus and binds it and then generates a colored product like this. Some of the colored products, like the ones I showed you, happen in liquid. There's another set of tests that happens on a paper strip that aren't very sensitive, but if you have someone who has a lot of Ebola virus, that it would be good enough. So it's possible it was one of those paper strip type tests.
Okay, so I'd like to announce winners real quick, and then we'll take another question, and then we'll hang out, do demos, and I'd encourage you to stop and get any snacks on the way out after you come up and have a chance to talk to Brian and see the device in action. So do we have ticket number 2041629, ends in 629, ending in 629, right here. All right, when you come up on the way out, you can pick up one of these light blocks kits, and we'll be expecting to see you in a couple of years in Brian's lab or in my lab. We then have a ticket ending in 627, ending in 627 right here. Same thing for you when you're coming on your way out. We've got a light blocks kit for you, and we're expecting a new spectrometer and a virus detection system by the end of the week. And then ending in 622, do we have Kit 622. We've got a winner right here, and for you, you're off the hook on virus detection, but we're expecting you to find cures for the diseases the virus causes. So just you have until 2 weeks from now, so don't worry about it. So with that, I'm going to let Brian answer a couple more questions, but I'd like to thank him for being here and giving a great talk. And thank you. So we'll take one or two more questions, and then we'll just empty the room and have everyone come up to see the demos. Thanks, Brian.
Thank you. Thank you. More questions? Yes? Oh, that's a great question. So people that are interested in detecting like pathogens in air, they have a front end that would sample the air before you perform the test. And so what they actually have are, imagine a big fan sucking in lots of air and gathering all the stuff in the air onto a filter. Then they wash the stuff off the filter and perform the test on that stuff. And so what you end up with is a liquid that's it looks like brownish green. It has whatever stuff that was floating around in the air. And it's mostly dirt, bug parts, whatever else. I mean, they have to be very sensitive to see a small number of like anthrax spores floating around in a sample like that. But the tests are sensitive enough that they can see like 5 to 10 in one small volume. But you have to actually suck them out of the air and get them into your test before you can see them. Oh, yes?
I was one away from 2 of the winning tickets.
Huh? that is hard luck.
No, I've got an International Bureau of Light pin for you anyway.
All right. Okay. Well, thank you very much. Oh, yeah, there's a question.
Can the camera see more than our eye can see, and does you take advantage of that?
All right, so the question is, can the camera see more than our eye can see? No. So the range of wavelengths the camera is sensitive to, they extend really in the visible part of the spectrum. The camera itself would be able to detect into the infrared, but the companies put a filter that cuts off in the visible part of the spectrum. Otherwise, you'd be able to use like infrared imaging to see through people's clothes and things like that, which they discourage. So, so that actually we would have liked to have used more wavelengths, but we would have had to do surgery on the camera to remove that filter, which is built into all of them now.
So I think actually we're going to hang out a little bit afterwards. I'd like to thank the speaker again, and come on up with questions for Brian. And for those of you who would like, we've got International Year of Light pins. Wear your International Year of Light.
Yeah, I think people probably come up to see it. Yeah, sure.
International Year of Light. Okay, so thanks for coming. Let's thank Brian again.
Illinois.